Why do you think it's important for the more traditional engineering firms to kind of, change how they approach structural assessment and monitoring of the building and things like that?
Yeah, I think because even for myself, before I started Sensequake, I didn't know on how much we can benefit from sensing solutions. Now that we are testing all these structures and we look at, the outcome that we had and the value we added to the projects, we see a lot of different cases that these solutions were essential to make sure we can have more reliable structures, we can reduce the cost, we can keep the structures longer in service.
When it comes to structural assessments and structural monitoring, we all know how crucial they are in ensuring the safety and integrity of buildings, bridges, and other infrastructure. It's an essential step in identifying potential risks, predicting maintenance needs, and ultimately saving lives. Join us as we sit down with Farshad Mirshafiei, CEO and co-founder of Sensequake, a trailblazer in the world of structural assessments, as we discuss innovative approaches and cutting-edge technologies that are transforming how we assess and ensure the safety of our structures. I'm your co-host, Matt Picardal.
And I'm your co-host, Rachel Holland, and this is the Structural Engineering Channel.
Farshad, thanks so much for joining us. Can you tell us about yourself and your career journey in structural engineering?
Sure. Thanks, Matthew and Rachel. Pleasure to be here. My name is Farshad. I am a co-founder and CEO at Sensequake. So I'm a structural engineer. And my background and the reason that I started the company and overall went to a structural engineering field is based on the fact that in our family, my father is an architect. From my childhood, I was going on site to different building construction sites. I was really familiar with this field. At high school, I was really strong in physics. So I was thinking, at university level, should I go and study physics or should I go in structural engineering? So at the time, I decided to go in civil engineering. And then later in the graduate studies, I went to structural engineering. So that's kind of the reason I chose the field. I think it's in our blood and, family background.
Awesome. Can you tell us what inspired you? So we're going to be talking a lot today about your company, Sensequake. So can you tell us what inspired you to start it and sort of, give us some insight into the vision that you have for your company ever since you started it?
Sure. Great question. So when I was going to all these, building sites, bridges, and I was talking to these structural engineers. It's civil engineering and structural engineering is a very traditional field, and there is not much innovation or forward-looking in our field. We mainly deal with standards, codes, so very, very traditional field. When I was gonna choose my graduate studies at McGill, I went to the group that they deal with sensing technologies and their applications in structural engineering. And I got familiar with different types of sensors and methods to analyze the data at McGill University. And my goal and my vision was always to bring a fundamental shift to this traditional field of structural engineering. So that was my vision. I was looking at mechanical engineers, electrical engineers, and how much innovations they bring to consumer-based products, which we don't have it in structural engineering. So that was the main motivation when I was choosing my research project especially during my Ph.D. at McGill. So I was working for a few years in sensing technologies and what we can achieve with sensors on buildings, on other type of structures. Then I came up with a new idea, and that later on it converted to a patent about how we can perform seismic evaluation of buildings just based on an ambient vibration testing. So at the time, it was around 2013 and 14, I started pitching this idea to the McGill community, to other structural engineers. I received good feedback. So 2015, when I finished my PhD at McGill, right away, I started Sensequake. At the time, if you want to be in sensing technologies, it's an interdisciplinary field. So I needed to have someone that is really good with electronics, and strong in math. So there was no one better than my brother. So he was working at the time at Ericsson. He had a Ph.D. in electrical engineering and was working at Ericsson. So I went to him, I pitched the idea. I told him, there is a lot of room for innovation in the structural engineering. And I convinced him to leave Ericsson and join Sensequake. So that's kind of our story on how we started Sensequake. I think both of us were very technical. Myself in the structural engineering field, my brother Merdad on electronics and electrical engineering side. So it was a very good fit. I have a strong passion in business, and I was involved in the business aspect of our projects from my, maybe from my high school time with my father. So that's also helped us, I think, to grow Sensequake together as I started taking care of a lot of business side, and he's more like a technical guy. So I think that was a great fit. And I think moving forward, we were able to attract good talent to our company. And 9 years forward, now we are an international company. We operate in over 15 different countries now. And we're involved in many landmark building, bridges, and other type of structures, which I think we can discuss more, later on what type of projects we do at Sensequake.
I love that this has kind of turned into a family business, even though it's international. So how many people do you have now that you employ? And are you and your brother still the main two people?
Yes, we are the main two people. We have a team about 20 people in our headquarters, but then we have a business model that we go into partnership with structural engineering companies around the world. So instead of opening satellite offices in different cities, we find structural engineers that are into technologies and innovations, and we bring them as a Sensequake partner. So we have these Sensequake partners now in different major cities around the world. They have our sensors. They bring it to their local clients, and they act as part of Sensequake business dev sales team. People that are in touch with the clients, they go and deploy the sensors. So that's our business model to grow, rather than just, having everyone just part of Sensequake. We think there is a need of ecosystem of structural engineers and the technology provider, which is Sensequake in this case, to work closely together to bring the best solution for the asset owner.
Yeah, that's awesome, because they obviously know the projects and everything like that that's going on in those cities better than anyone. So that's a great partnership. I like that.
Yes, exactly. So that has really helped us to grow exponentially in the last couple of years, and be able to have all these projects in different countries. You need to have that network of people.
Where are you guys? Oh, sorry, Matt. One other question. Where are you guys actually located then? Your headquarters?
Yeah, headquarters is in Montreal.
Okay.
And yeah, the headquarters is in Montreal. But as I said, we are very active in US and different regions in US, all across Canada, in Mexico, South American countries, in Europe, in France and Italy, then in Middle East, in Saudi Arabia, in Qatar, and then Asia, Japan. We are active. So
amazing.
Yeah, I was curious more about what the sensors for Sensequake. What specific problems do they solve? Where the engineers, you eventually make them the partners. Do they have a sense of, we need to, maybe it's a code requirements for trying to figure out how the building behaves during seismic activity? Are those types of things that your clients essentially want, and that's what the Sensequake sensors solve?
Yeah, great question. So initially, when we started Sensequake, we started it as more on the software side, that we have algorithms that can predict a building seismic performance just based on an ambient vibration testing. And we were using third-party sensors. And when we started, talking to all different asset owners in US, different DOTs, bridge owners, building owners in Canada, we figured out that actually the sensors that are on the market, they weren't necessarily the best fit for a structural engineering community. They weren't sensitive enough. They weren't wireless. They weren't easy to be used, and they were very expensive. And we figured out that if we want to bring a fundamental shift in order to really expand the number of applications of sensing technology, we need to have a vertical business that we are the manufacturer of the sensors and creator of the software to bring an ecosystem that can be used by structural engineers and asset owners. So we started developing our own hardware in addition to our software package. And also, this was a very good combination. Because if you look at the current ecosystem of sensing technologies and vibration sensors, for structural engineering, normally the focus is on gathering just the raw data. They don't do much with the data. And I think one of the reasons is the founder of those companies, they're more electrical engineers. So they don't know exactly what the structural engineers need. I think for us, we had this unique opportunity that my brother and myself, we complement the backgrounds that we have in structural engineering and electrical engineering. With that mindset, we built technologies that are based on data-driven analysis, that we can extract features out of the data that can detect, locate, and quantify damage in different types of structures, not only due to natural hazards, but also aging. So when we started Sensequake, the focus more was on earthquake engineering side, but now Sensequake is about data analysis and sensing technologies that can identify and pinpoint any structural anomaly, whether it's due to aging or any type of natural hazard. You may have, fire in the structures. We have clients that they have fire, they come to Sensequake and ask, what's wrong with my structure now? We have people that they have foundation issues. We have a lot of bridges that they use our technologies, DOTs, California, Indiana DOT, multiple Ministry of Transportation in Canada, in Saudi Arabia, in Mexico. They use our technologies to understand what's the issue with the bridges, issues that they cannot visually see, or a lot of surface damage that, every time you're driving on a bridge, you may see, some spalling of concrete, some corrosion. So the question that the bridge owner has, should I do a rehabilitation? Should I do a replacement? Which bridge should I invest? We know in the US, we have a lot of deficiency within bridges, and you have a scarring issue. So we can help them with those. And on the natural hazard side, we have technologies that can predict what's going to happen to a building before an earthquake hits. We have technologies that we mount them on structures permanently. So when an event happens, we do real-time analysis and we send automatic reporting to the asset owner to let them know if the building is damaged in the structural side, in the non-structural side. We color code the building, and we have technologies that can do very sophisticated analysis in real time. So that's what Sensequake does. So we have multiple different sensors and web-based software packages. So we have different technologies.
I was going to ask that. So is it like, depending upon what you expect the building to see in its lifetime, you choose a certain sensor and software package for that? It's not all just one sensor that can do it all?
Yeah, so we have 3 types of sensors and we have 3 types of software. So we have 6 different products. And as you said, based on the scope of the project and need of the client, we decide which package, which solution is the best one. So if someone comes to us and say, I have a bridge, I want to know these corrosions that I see, is it something that I have to fix? And when should I fix, right? Then we use different types of sensors that can help us to really quantify the damage for them. And that actually we can achieve by having just sensors on the deck level of a bridge. Normally we put the sensors on the shoulders, and for just a few hours, then we have a different software that does the data analysis to really let them know what's wrong with the foundation or superstructure, bearings, and so on. If someone comes to us and say, I have this governmental building, high assets in a seismic region, and what I want to know is what's happening to my building if there is an earthquake. Let's say we have clients in Japan and that's what they want, or in California, right? And whenever there is an earthquake, our system does automated analysis. And the analysis is really similar to a very detailed finite element model, but everything is sensing based. So that makes it very interesting, because the other technologies, when you have these permanent sensors, let's say you have few sensors in a hospital in California at the moment. Normally what happens is after an earthquake, they give you the records, the vibrations. That's not what we do at Sensequake. So after an earthquake, we do a full analysis on our servers. So we have the building model already built and everything is sensing based. We don't make finite element models. We don't need to have a structural drawings. Everything is sensing based, and we can still do a full analysis of the structure to replace that 3-4 months of a need of a structural engineers to go through the drawings, make those finite element model. We do it just based on sensing analysis. So we have another patent on how we can just put few sensors on the building and still do a very sophisticated analysis in real time in order to compare the seismic demands, the drift ratios and accelerations with different fragility curves from standards to create that type of color coding of a structural and non-structural components after an earthquake. So really, we have very advanced way of looking at data analysis.
Yeah. So interesting.
Yeah. So for that one, that's I'm in California, so very familiar with earthquakes. So that's a really interesting topic for me. So would that work? So let's say that hospital example, if an earthquake hits, then if those sensors are already in place, would they be able to know if the seismic system or any type of structural system that you're recording, would they be able to know like in real time if that building's immediately safe or occupiable or damaged, like right after an earthquake? Or would they still need to get a structural engineer out there, do assessments?
Yeah, so they're going to know right away after an earthquake what's wrong with the building, if there is anything wrong with the building. And that is not just based on the data that we're gathering at the sensor location. It's really based on a very sophisticated model that is being run in real time. So normally we have at least one sensor at the base of the building, which is getting the actual earthquake. So that comes to our web-based dashboard, in real time. Then we have the building model already built. It is not a finite element model. It is sensing model. Then it's similar to your finite element model. We do time history analysis, if you guys are familiar with those concepts, but it's based on a sensing model. And we consider all the changes in the building and soil structure interaction as part of our models based on real data that we are capturing with the sensors above the base of the building, let's say on the different floors and the roof that we normally have other sensors. And based on that, we do the whole analysis everywhere on the building, even non-sensor locations. And so it's a full analysis that is being done in real time. So normally within 2 to 3 minutes, you receive a very comprehensive report with all the engineering demand predictions. Let's say your drift ratios and acceleration levels at sensor and non-sensor locations. You see all the EDPs. You see the comparison with fragility curves from FEMA P58 and all these different standards. It's already built inside the model. And then you see the color coding of the building. So the first few pages is very high level for the owner to know what they should do. Should they evacuate? Can they go inside? Which floor, which corner there is an issue? And the appendix could be 100-page, similar to a very advanced, software. You have all these EDPs, different comparisons, and so on. So it's a completely different way of looking at sensing technologies. That's what I am trying to convey to different structural engineers. I was an invited speaker at Portland just 2 weeks ago for CIOSC.
Oh yeah.
And there I was just, sharing the same experience that we have at Sensequake, that now with all these technologies and novel sensors that are wireless, you can measure hundreds of locations on a structure. You can put sensors permanently on the structures, and we have data-driven methods that can really help our industry to understand the structure in a way that we weren't capable before. And then this helps us to create databases to better perform integrity evaluation. So that database is a key. So we need support from different stakeholders to improve that database of structures that are either temporarily instrumented or permanently instrumented. And at Sensequake, now that we have thousands of bridges in our database, thousands of buildings in our database, that database is really helping us to really pinpoint the issues within the structures. So we hear about these data-driven methods in other industries. I think civil engineering is one of the industries that can benefit the most if people are going to be more open into innovations.
Yeah,
Right.
thinking of just the cars, right? With the electric cars, they have all that data on self-driving cars, for example. They do a lot of lessons learned. But in civil structural engineering, we build the building. We won't know if it's damaged until an earthquake hits or something hits. And it's more of a, oh, that looks damaged. I'm guessing this is what happened to it. You don't really know how it behaved, but now it seems like there's that technology there where we can get all of that data to see what these types of structures actually behave like.
Yeah, we're just going to add, we build all these beautiful structures and then we leave them alone. And every structure is different. We have to track their properties from day one. So now we're talking to a lot of, codes and the standards in the US, in Canada, to add these sensing solutions as part of the code, because it's the best way to make sure it can be used everywhere on a larger scale. And then we can track them, and you don't even need a natural hazard to have failures, right? We saw what happened to Surfside building in Miami. If a technology like Sensequake was installed, we could have told them in advance that your building is going to have that much damage. Or recently we worked on another bridge in California, and it was a 100-year-old bridge, and they had some issues with the soil. We tested the bridge. We told them exactly what's wrong with the bridge. We pinpointed the issue, and the owner was going to rehabilitate the bridge at the locations that they had the scarring. But then we had Hurricane Hilary just happened a few months after. They didn't have enough time to do the fixing, and the bridge collapsed exactly at the location that we predicted. So if they knew about the technology sooner and they were using the technology, then they could have kept that bridge in place, and now the bridge was still around. So I think that's a message for other DOTs and other building and bridge owners, that these technologies now exist. They can add huge value. There are other case studies now how these technologies are being used on buildings and bridges, and they can really benefit from it.
Yeah. So we've talked a lot about kind of like traditional civil engineering and how it's not always been the most innovative and kind of like progressive in terms of technology. Why do you think, I do think there's a shift. I think you're part of it, obviously. I do think there's a shift, and that is actually really exciting to me. But why do you think it's important for the more traditional engineering firms to kind of, change how they approach structural assessment and monitoring of the building and things like that?
Yeah, I think based on, because even for myself, before I started Sensequake, I didn't know on how much we can benefit from sensing solutions. Now that we are testing all these structures and we look at, the outcome that we had and the value we added to the projects, we see a lot of different cases that these solutions were essential to make sure we can have more reliable structures, we can reduce the cost, and we can keep the structures longer in service. And I think a lot of other industries, they're using technologies much more than civil engineers. It's probably more due to standards and codes that, are kind of making it really hard for innovations to be adopted on a larger scale, because you have to go through those codes. And by default makes the structural engineers more conservative in what they want to do, which I think is always a dialogue I'm having with people that are involved in the codes and, standards, that we should think about how we can bring these new technologies, emerging technologies, as part of the codes and the standards and in our field. I think it can really help. If we look at, civil engineering, if we are talking about performance of the structures, the current practice hasn't been optimized way of looking at performance. Either, we look at the service life of assets and aging, we see other bridges and buildings that they have problems. We're going to face the same issue 50 years from now if we go with the same approach. If we look at natural hazards, every time there is an earthquake, there is a hurricane, the structures are not showing the performance that we expected. And there is a lot of reasons behind it. It's not really the fault of the structural engineers. It's the methods that are being used and the assumptions that they go in place when we build something versus what we assume in our models, right? So inherently, there are differences. So if someone has ever done, a research at university or worked on those shake table tests, they know what they assume in their models is very different than reality. And that's why the performance of structures, they don't match the assumptions of engineers. And I think put everything together, we need to use technologies to build structures that they can last more. And we can be on top of their performance, right? Let's say, I give you an example. I think on a plane, we have on average about 10,000 sensors on a plane. I think in a car, you have hundreds of sensors. In buildings, we almost have zero sensor related to a structural integrity evaluation. And the other interesting part is if a car company wants to make and manufacture a new car, they do all the tests, they put all these sensors, and then they build the same car over and over. In civil engineering, every building is unique. You have architects, they design different buildings. We just build them. No building is the same. And we never test them, right? We just build them. We move on to the next one. So I think that's the mindset that needs to be changed, and it takes time.
One thing that comes to mind is I remember I was at a convention where someone during the Turkey earthquakes, they did a whole bunch of reconnaissance on the hospitals there. And one thing that maybe structural engineers don't worry too much about was right after a hospital earthquake, the occupants need to make a call on whether to shut the building down or continue operations with the hospital, which is a big deal during an emergency event. And so they would find out that the people in charge of the hospitals, a lot of the non-structural components would get damaged. So it looks like your building isn't safe. But they didn't have the time to, get a structural engineer. It's an emergency, a national emergency. They don't have the time for a structural engineer to come in, make the structural assessment. Is a hospital okay? They just needed to make those split-second decisions on the spot. And I think some hospitals ended up just shutting down just because the non-structural components looked pretty damaged and scary, but all the structural components were still fine. But they shut the hospital down. And during emergencies like that, I'm pretty sure a lot of people lost their lives just because they couldn't tell whether the structural systems were okay. So that's one of the things that comes to mind where, oh, that's cool. Like during an event like that, emergency event, those sensors could really help them make those decisions.
Well, yeah, it lets us move beyond like a visual observation, right? Like we get more information, which is always helpful.
Yeah, so that seemed pretty cool where we have technology like that now where normal people or more normal people, non-engineers can get better introduced or make better judgment calls on that. So that seemed pretty cool. And does that, in terms of how it works, is because you were mentioning that you would have sensors, but it almost seemed like non-destructive testing kind of where you put vibration through it and then do the sensors through your technology and algorithms based on, I guess, how the frequency, how it moves just from that small little vibration. You can kind of interpolate how the overall structures is, or if it's damaged in one specific spot. Is that kind of how it works?
So the way that we can address this is by combining two types of tests that we do at Sensequake. So normally the first thing we do when we have a building, we come up with, we send some people to test the structure on every floor. So we're going to put on average about 200 sensors in a building. So we get already a very detailed snapshot of that structure. And that really helps us to understand the building to all the details that it has. Then based on the results of that test and analysis, we decide where we want to put the permanent sensors. We may just put 2 or 3 permanent sensors, or sometimes we may put 10, 20 permanent sensors, depending on what is the goal of the client, what type of natural hazards they have. Is it just earthquakes? Sometimes, you have blasts, you have hurricanes and so on. And is it aging? And then when you have those sensors, the real-time monitors, their analysis is combined with the pre-analysis phase that we have done on the structure using that detailed rapid testing that we have done before. So these are two complementary systems that we are combining: a very detailed test with a lot of sensors, and then a permanent system with a lower number of units. So they work together hand in hand. And that's the way that we have achieved to really analyze the whole structure in real time by having a limited number of sensors. So that's actually one of the innovations that we have done at Sensequake, is to combine these two solutions. And that's an essential part of, using technologies that can provide actionable insights. As you said, let's say in our reports, we have a section talking about structural performance during an earthquake. There is another section talking about non-structural components and what happened to those components. So the owner can see that in their reports. They can see the location. They can see the different floors, and they're going to know what's the best next step, just 2 minutes after an earthquake happened. So that's how we address this this issue. Yeah.
Can you tell us a little bit? I mean, you've mentioned a few of the projects that you've worked on, and you've got these sensors in thousands of buildings and bridges around the world. What are some of the more notable projects that you guys have worked on that, Sensequake their solutions have helped with, like the safety and maybe even provided cost savings for the clients or things like that? What would you say, like, top couple projects that you want to mention?
Sure. I think on the building side, we have Parliament of Canada, we have Supreme Court of Canada. So all these, high value assets. I think we look at one of the, interesting projects that was done last year, the 10-story building at UCSD, the shake table test, the tallest building ever built on a shake table. That our technologies were involved. And I think there were about 86 earthquakes that were applied to the shaker. And every time our system was triggered, created the report, and everything was matched with what was happening in reality. So it was a very successful case for us. And let's say Port of Long Beach is using our technologies on wharves, on buildings. We have these very landmark assets for governments in Japan. But those are, confidential projects. I cannot name them. But we have those projects as well. On the bridge sector, we have Champlain Bridge is one of the largest cable stayed bridges in North America. We have Jacques Cartier Bridge. We have multiple bridges for Indiana DOT. I mentioned another bridge in California, which was an interesting case as due to what happened to the bridge after we have been testing that bridge. And so there are all these buildings and bridges. On the other infrastructure type, let's say Hydro-Quebec is using our technology on dams. There is a company called Geosyntec. They're using our technology on dams in California. Then, as I said, ports, they can benefit from the technologies as well. And actually, a lot of universities in North America, they are adopting our sensors and software for research purposes. Let's say University of Georgia, University of Memphis, UBC, University of Windsor, Concordia, all these different universities, they are using our technologies for research purposes as well. Overall, what we think is, researchers are very important, the structural engineers are important, and the asset owners are important, and we have to work with all of them in order to make sure we can bring a change to civil engineering and structural engineering.
Yeah, it's great. I mean, I feel like you really tapped into a niche thing that is elevating, it's elevating the standard to which we build to, right? It's going to change things. I have a follow-up question for you on the UC San Diego testing.
Yes.
I was able to go down there the second for the 6-story one. So it was after the 10-story one. And I remember Steve Pryor talking about how they hadn't had to change out the links and different things with the structural lateral system. And it'd been run multiple times in these tests. Was that part of your sensing that was able to determine that they didn't need to swap those out and they were all still structurally sound?
Yeah, so interesting question. So they were structurally sound. That being said, any structure goes through changes when you have higher shaking levels. There are changes that you may visually not see, but the structure goes through changes. So let's say the building that you are in now, if you have a small earthquake, the building properties, they're going to be changed, even if there is no damage. And that's one of the reasons we have to monitor structures to take those into consideration when we do something to the structure in future. If you want to retrofit your building, you have soil structure interaction, which, I mean, there was no soil at the 10th story, but the structural properties, when we look at the structural properties, there are some major properties that they were not changed in the case of 10th story, which indicates overall the structural integrity was sound. That being said, for some higher modes of the structure, there were changes. And especially there were changes, if you remember, I think there were non-structural components in the first 4 levels of the building. And we saw changes in those levels, which was due to the changes to non-structural components. So when we look at these signatures and these information that we get out of the data, we can tell the owner, look, let's say the structural system is almost sound. There are some changes, but your non-structural components were at these, 3-4 levels. They have gone through changes, and we can see it in the dynamic properties or different properties that we're extracting from the structures. So there were non-structural component changes. There were some minor structural changes. So normally the structure gets relaxed due to all those, bolts and connections that you have. It's not necessarily a damage, but the structure goes through changes. So that structure also went through some changes, but it doesn't necessarily mean it's break.
For your analysis then, and like the reports that you give to your clients, you'll say like changes occurred, right? And then are you making the determination about whether or not it's considered damaged or not damaged, or like risky to keep it intact, or you need to change, you need to fix it? Is that something that you guys...
Yes.
Okay.
Yeah, we do that. And that's the final portion of our methodology. And the way we do it is by comparing our analysis results with fragility curves that are in different standards. Let's say FEMA P58 is one of the standards that has all these fragility curves. And fragility curves are determined, by a lot of, lab tests. So let's say you put different components of a structure or non-structural component on a shake table, you shake it, and you create a fragility curves, which tells you for different drift ratios or acceleration levels, what type of damage you're going to observe in that particular component. So that is predetermined. So we bring that into our dashboard, and that's already set in our dashboard. So when we analyze the structure in real time, then we can compare the demands versus these fragility curves in order to tell the owner, what do we think happened to your bracing system? What happened to your bolts? What happened to your suspended ceilings, to your equipment? So we use those fragility curves. I think at the moment in FEMA P58, there are about 800 components from all, shake table tests that was done in the last century. They combine everything. And there is a lot of components that are still not there, but it's in the literature. So we take advantage of those as well. So whenever there's a shake table test around the world, we bring those information as part of our database. So we're combining multiple different databases from the structures that we have tested, from shake table test, and from the buildings that are permanently instrumented by USGS, by other organizations. As we are in a data-driven world, we are trying to take advantage of every data that is that we can, get a handle on it. So we bring them to our methodology.
Yeah. And what do you think the structural engineering industry with regards to the integration of these technologies, how do you think it'll look like in, 20 years? What's the future vision for that?
Yeah, I think about it from time to time. So that's a good question. I think, and hopefully it's going to be Sensequake as part of this change. We're going to see, maybe even not in 20 years, in the next few years, a software that can design and optimize a structural system for structural engineers. I think we're still going to need to have structural engineers to check the final design. But the way that we use the finite element models, and we're using different components inside the structure, let's say you have 20 different building types in FEMA, you have wood, you have steel, and different types of steel structures. And we have all these codes and the standards, but it's a repetitive process. So it is completely feasible. Actually, we have looked at it inside Sensequake as well for maybe future developments, that it is completely feasible to use machine learning and data-driven methods to take advantage of all this information to design and optimize a structure in terms of cost and performance based on the location, based on different factors, to make sure we have an optimized design. So basically, the software is going to go through iterations to try to build that structure for you that is going to be optimum in terms of cost and performance. And that software is going to take advantage of all these data from permanently instrumented structure, all these tests, in addition to the finite element model. So that software can do a lot of more iteration that, as compared to a very experienced structural engineer that may just think about 2 or 3 iterations, and they may not have really access to all these databases. But that software that is combining, real-time data versus the finite element world, and combine both and can go through all these iterations to automatically design and optimize a structure, which probably at the end, just a structural engineer is going to check to see if it's good. And maybe at some point, it goes directly to the contractor, I think further on the road, but there are steps. But I think that automation is going to come. Again, because I think in our field, innovations are hard to be adopted due to the codes. It's taking longer. Otherwise, I think by now that type of technology would have existed, as it is totally feasible to automate the whole process.
Yeah, we got everything in the code, step-by-step process. We just don't have the tech money, right?
Yes.
to pay a bunch of programmers to do all the research on this.
Yeah, I think we have enough information now to make sure you tell the software, I want a 5-story building in LA. Give me the best building and the components, and it can go and choose the best, affordable in terms of cost and also performance. So that's possible.
That's the interesting thing. Linking I think that's the thing that we're missing in our software, that link to real data, real world data from how structures actually behave. That'd be really interesting to see how that gets implemented into design, but the data's getting there. So
yeah,
sure.
I love hearing your forward thinking topics though, and how you're thinking it could change, because our industry is slow to change, but it is changing. So, okay. So one last final question for you that we ask is, do you have a piece of advice for engineers on how they can adapt for the changing landscape that we have in our industry and for their career?
Yeah, I think be open to innovations. Be open to go out of your box and see what is out there and how it can benefit the whole industry as a whole, asset owners, engineers, and everybody, every stakeholder that is involved. I think we should learn from other industries. We see, how quickly they're adopting technologies, and they go from technology 1 to 2 to 3. They don't use the same finite element software package for 50 years. I think that's very rare. I mean, we have it in our field. So I think there should be much more openness to new technologies. I think codes and standards are great to make sure the quality of the design is kept in place. But at the same time, there should be room and a process in place to adopt technologies faster through codes and standards. I think that's also a missing portion, that they need to think about a way to vet these technologies and be able to use them and adopt them faster in place. But I think we're going to get there. I see a lot of young people and young generation that they're open to innovations. They see innovations coming every day. They hear about AI, they hear about data, they hear about sensors. Obviously, that by itself brings a lot of questions to people's, mind, that why we are not using it in our field, and they become, I think, naturally more open to technology. So I think the new generations of engineers are going to be the future leaders as well.
Yeah, I totally agree. I think that's great advice. And I was just gonna say the same thing. In my role, I'm lucky enough to be able to interact with a lot of students and younger professionals. And I really feel like they are open to change and seeing things progress on the tech side of things. And like you said, I think it's going to change our industry, and it's going to be exciting to see.
Yeah, exactly, Rachel. I think we also have to collaborate with other fields. Let's say in our company, Sensequake, we have obviously structural engineers, but then we have mechanical engineers, we have electrical engineers, we have software developers. So when you have the interdisciplinary team and you get the view of these other talents and other, people, then I think it helps you to also bring more innovations and changes to your own field. So I think that interaction is important as well to try to learn and interact with other disciplines. I think that helps.
100%.
Yeah.
Totally agree. Okay. Any other follow-up or anything else you wanted to add?
I think we went through everything. I think it was a great conversation here with you, Rachel, and Matthew. I think yeah, it was fun.
Well, we wanted to thank you so much for joining us on the show and being a guest and sharing all your expertise. And it's been a pleasure having you on the show. So thank you.
Yeah, pleasure was mine. So thank you. It was a great experience for me.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, as well as any links to any of the resources or websites mentioned during the episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you all the best in your structural engineering endeavors.